Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to introduce myself. My name is Budi Prabowo Soewondo. I'm from the Pharmacy Department at the Faculty of Mathematics and Natural Sciences, Universitas Islam Bandung. I would like to give a 10 minutes presentation at the SiRes, or Science and Technology Research Symposium, that is being held by Universitas Islam Bandung. And here is my presentation. My presentation is entitled Vibrational Spectroscopic Activities of Molecules with D3H, D4H, and D5H point group symmetries. As we know, vibrational spectroscopy is actually one of the fingerprint of molecules, and there are two kinds of vibrational spectroscopy. They are the infrared or IR spectroscopy and Raman spectroscopy. Now, for a relatively simple molecule, the method of group theoretical analysis is sufficient to determine the vibrational optical activities of the molecule. Now, for the analysis of the spectroscopic activities, if we want to analyze the IR activities, we need to evaluate this integral. And if we want to evaluate the Raman activity, we need to evaluate this integral. Now, these two integrals are actually similar, but the difference is actually at the operator in the middle. This one is the electrical dipole moment operator, and the alpha is actually the polarizability tensor operator of the molecule. Now, the way this method works is actually can be summarized by these steps below. First of all, we need to identify the point group symmetry of the molecule and assign the vectorial representation of the group as gamma vec. And then we need to find the number of atoms in the molecule that are unaffected by each of the transformation in the point group symmetry of the molecule and assign them as the atomic site representation gamma AS of the point group of the molecule. And then we need to determine the molecular representation given by the direct product of the gamma vector and the gamma atomic site. Next, we need to extract the molecular vibrational representation by subtracting from the molecular representation here given by the direct product the translational and the rotational representations. And then after we got this molecular vibrational representation, this is actually the transformational properties of the wave function gamma nu. Now, what we need to do is we actually need to analyze the transformational properties of the integrand of the transition probability amplitude. Here are the integrands that were given. And these are the transformational properties of the integrand, right? These are the wave function. The gamma mole is actually the wave function transformational properties, and the gamma mu and the gamma alpha is actually the operator transformational properties. Now, after we calculate the direct product of the integrand, we need to decompose it to their irreducible representations. Here is the symbol, and we need to work it out in the character representation given by this direct sum. And the most important part, we need to find the number AI, and the number AI, or the constant of the direct sum, is actually given by this formula. This formula is we get this formula from the wonderful orthogonality theorem of the group theory. Now we need to show that whether the AI for A equals 1 is actually 0 or not. If it's not 0, then the sum contains a totally symmetrical representation, then the molecule is IR or Raman active. Now here the definition of the DNH point group symmetry. The DNH is the direct sum of Dn, dihedral group Dn, direct sum by sigma h. Sigma h is actually the horizontal reflection operator. Now here are the D3H point group character table, and from this table we can extract the relevant representations given here, the translational, rotational, and the operator's representation from these columns, 2 columns here. And here are for the D4H point group symmetry. Here are the representations that are relevant for our calculation or our analysis, and here are the relevant representations for the D5H point group symmetry that is being extracted from this character table. These are actually the integral that we need to analyze for the fundamental transition, or the transition from the ground state to the first excited state of the vibrational wave function. Here we replace nu by 0 and nu prime by 1. Now we have a simpler form of the transformational properties of the integrand. We actually only need to analyze this first excited state molecular vibrational representation times the operator's representation. Now here is the analysis of the D3H point group symmetry ozone molecule. From this character table of vectorial atomic site and molecular representation, we get this direct sum, and this for the vibrational molecular representation, and then we analyze the integrand transformational properties by this direct product here. And if there are elements in common from the molecular vibrational representation with the operators, then that means we got the totally symmetrical irreducible representation as the direct sum here, and then the molecule is IR or Raman active. Now for the ozone molecule, we have the E' molecules in common for the molecular vibrational representation and the operator representation, which means that the E' mode of the E' vibrational mode is IR active, and for the Raman active, the vibrational modes that are Raman active are A1' and E', here given below. And for the PF5, the same D3H point group symmetry, we find the same analysis, and we find that the vibrational modes that IR active are E' and A2 double prime, and the Raman active vibrational mode is actually A1', E' and E double prime. So this molecule PF5 is a Raman active and IR active. Next, we analyze for molecules that have D4H point group symmetry. First, we analyze squarine. This is actually a fictional molecule. For this simple molecule, we get this direct product that we need to analyze, and we find that the squarine is actually IR inactive because there is no element in common between the two representation of the molecular vibrational representation and the dipole moment representation. So between these two direct product, there are no elements in common. The squarine is a Raman active with the vibrational mode of A1G, B1G, and B2G. Now there is a vibrational mode that both IR and Raman inactive, and that vibrational mode is the mode of B2U. Next, for the D4H point group symmetry, we analyze the xenon tetrafluoride molecule, and from these two direct product, we find that the XeF4 is IR active with the vibrational modes of A2U and EU, and Raman active with the vibrational modes of A1G, B1G, and B2G. And there is one vibrational mode that is both Raman and IR inactive, and that vibrational mode is B2U. And lastly, we analyzed a molecule with D5 H-point group symmetry, that is IS7. And from this analysis, we come to the conclusion that the IS7 is actually IR active with the vibrational modes of A2 double prime and E1 prime, and also Raman active with the vibrational modes of A1 prime, A2 prime, A1 double prime, and the vibrational mode E2 double prime is both Raman and IR inactive. So in conclusion, we have found that the group theoretical methods is indeed a powerful tool to determine the vibrational optical activities of simple molecules. The method can give the vibrational modes representations that corresponds to IR and Raman transition, and the method also can give the vibrational modes that is not IR and Raman active for fundamental vibrational transitions. Here are the references that is being used in this work, and that is all. Thank you. Assalamualaikum warahmatullahi wabarakatuh.